Beyond Neptune, trillions of frozen objects drift in silence. They have been circling our star for over 4 billion years, undisturbed, predictable, until now. Scientists discovered that something out there is pulling on these ancient objects, bending their paths, tilting the very shape of the region they call the Kuiper Belt. Whatever is doing this, we cannot see it. No telescope has captured it. No spacecraft has reached it. But the evidence says it is real, it is massive, and it is closer than anyone expected. If you enjoy journeys like this, tap like and subscribe so you do not miss what comes next. Take a breath. We are heading into the deep. Picture the edge of everything you know about our solar system. Go past Mars, past Jupiter and its crushing storms, past Saturn and its glowing rings, past Uranus and Neptune, the two ice giants that barely get any attention. Keep going, way out there, starting at about 30 times the distance between Earth and our star, you hit a wall of cold. A massive ring of frozen debris stretching billions of miles in every direction. This is the Kuiper Belt, and most people have never even heard of it. It is more like a cosmic junkyard, a sprawling donut-shaped zone packed with hundreds of thousands of icy bodies, some as small as a house, others as wide as a small country. These objects are made of frozen water, methane, and ammonia mixed with rock and dust. They are leftovers, scraps from the construction of our solar system over 4.5 billion years ago. Think of it this way. When the planets formed, the leftover building material drifted outward and settled into this frozen ring, and it has been sitting there, mostly untouched, ever since. A graveyard of things that never became planets. The Kuiper Belt is enormous. It stretches roughly 20 times wider than the asteroid belt between Mars and Jupiter, and it holds 20 to 200 times more mass. Scientists believe there are over 100,000 objects out there wider than 60 miles across. Dwarf planets like Pluto, Haumea, and Makemake all live in this region. So do countless smaller chunks of ice and rock that have been drifting since the very beginning. If you could somehow gather all of them together, you would have enough material to build a world several times the size of Earth. Yet most people have no idea the Kuiper Belt exists. That is partly because it is so far away that even our best telescopes can barely see what is out there. Only one spacecraft, NASA's New Horizons, has ever flown through it. In 2015, it sent back the first close-up images of Pluto, revealing mountains of ice and glaciers of frozen nitrogen on a world everyone thought was dead. Then it kept going, flying past a small snowman-shaped object called Arakoth deeper in the belt, and what it found changed our understanding of the outer solar system forever. Here is what makes the belt so fascinating. It holds some of the oldest, most unchanged material in the entire solar system. These icy bodies are frozen time capsules from the very beginning. By studying them, scientists can peer back to the moment our neighborhood was born. That alone makes the Kuiper Belt one of the most important regions in all of astronomy. But here is the thing that keeps scientists up at night. The objects in this belt are behaving in ways they should not. Their orbits are bending, their paths are shifting, and the deeper we look, the stranger it gets. Something is out there, hiding in the cold, pulling on the Kuiper Belt from a place we cannot see, and whatever it is big enough to reshape the edge of our entire solar system. Before we chase that mystery, we need to understand how we even got here, and that story starts with a tiny, frozen world that lost its title. What happened to Pluto changed everything we thought we knew about the edge of the solar system. For 76 years, Pluto was the 9th planet. Discovered in 1930 by a young astronomer named Clyde Tombaugh, it sat at the edge of everything we knew, a tiny, icy dot at the far end of the solar system map. Generations of kids memorized it in school. Textbooks printed it. Pluto was the underdog planet, small but official. Nobody questioned it. Then, in 2006, the International Astronomical Union did something that shocked the world. They took Pluto's planet status away. Overnight, our solar system went from 9 planets to 8. People were furious. Protests popped up online. Scientists received angry letters. But the decision was based on a simple realization that had been building for years. Pluto was not alone out there. It was just the most famous member of a much larger family. Starting in the early 1990s, astronomers began finding other objects out near Pluto's orbit. First one, then dozens, then hundreds. These icy bodies were scattered across a region that matched predictions made decades earlier by scientists who suspected a belt of frozen debris existed beyond Neptune. In 1992, the first confirmed Kuiper Belt object was spotted. It was a small, dim chunk of ice called Albion. It was nowhere near as famous as Pluto, but its discovery opened the floodgates. The outer solar system was suddenly crowded. More objects followed. Some of them were enormous. In 2005, a team led by astronomer Mike Brown discovered Eris, an icy world that turned out to be more massive than Pluto itself. That discovery forced the question nobody wanted to ask. If Pluto is a planet, then what about Eris? And what about the dozens of other large objects being found in the same region? The solar system was filling up with candidates. Either we had to call them all planets, or we had to change the definition entirely. The astronomical community chose to rewrite the rules. Pluto became a dwarf planet, one of several in the Kuiper Belt alongside Haumea, Makemake, and others. It was a painful moment for anyone who grew up with 9 planets on the classroom wall, but it was also a turning point. Pluto's demotion forced us to look more carefully at the Kuiper Belt itself, and what we found was far stranger than anyone expected. Because once we started paying closer attention to the belt, we realized something deeply unsettling was happening. These frozen objects were moving in patterns that should not exist. Their orbits were aligned in ways that defied chance. Objects separated by billions of miles were pointing in the same direction, as if arranged by an invisible force. And the only explanation that made sense was one that nobody had proven yet. Something big was hiding out there, pulling on the ice, shaping their paths from a distance we could barely imagine, and we were just starting to notice the signs. The first real clue came from a handful of orbits that broke every rule we thought we understood about how distant objects should behave. In any normal part of the solar system, objects drift along their own unique paths. They loop around our star at different speeds, different angles, and different distances. Over billions of years, gravity stirs them into a random scatter. No pattern, no alignment, just chaos doing what chaos does. That is how orbits are supposed to work. Randomness is the default. But in the outermost reaches of the Kuiper Belt, something strange started showing up. Around 2014, astronomers noticed that a handful of the most distant objects beyond Neptune shared something unusual. Their orbits were clustered. They were bunched together, pointing in roughly the same direction as they looped around our star. It was as if invisible hands had arranged them on purpose, and the pattern was too neat to ignore. Now, a few objects lining up could be a coincidence. Space is big, and patterns sometimes appear where there are none. Scientists know this. They are trained to be skeptical of anything that looks too convenient. But the more they looked, the more objects they found in this same suspicious arrangement. 6 of them, then more, all orbiting in elongated loops that stretched far beyond the Kuiper Belt, and all tilted and aligned in a way that probability alone could not explain. These were not small rocks. They were ancient, icy bodies, hundreds of miles across, and they were all pointing the same way. Think of it like this. Imagine tossing 100 marbles onto a spinning table. You would expect them to scatter everywhere. But if you came back an hour later and found a dozen of them rolling in the same tight circle, you would know something was guiding them. That is exactly what scientists were seeing in the outer solar system. Except, instead of marbles, these were frozen worlds the size of small countries. And instead of a table, this was the edge of our solar neighborhood, stretching across billions of miles. The numbers backed it up. Statistical analysis showed the odds of this alignment happening by pure chance were extremely low. Something with serious gravitational muscle had to be shepherding these objects into formation. Neptune was too far away to be responsible. Its gravity fades long before reaching these objects. The other known planets were even farther from the action. Whatever was causing this had to be out there with them, lurking in the dark, unseen and completely undetected. An invisible force operating in a region we barely understand. This was the first real clue, the first whisper that our solar system might be hiding something massive beyond the reach of our telescopes. And once scientists started listening, the whispers got louder. Independent teams ran their own analyses using different methods and different datasets, and they kept arriving at the same disturbing conclusion. The clustering was real, it was statistically significant, and it demanded an explanation that our current map of the solar system simply could not provide. Something was missing from the picture. The orbits were just the beginning of the puzzle, because soon, researchers found something even harder to explain. The entire shape of the outer solar system was bent, and nobody could figure out what was bending it. Our solar system is roughly flat. The 8 known planets all orbit along the same plane, like grooves on a spinning record. This plane has stayed stable for billions of years, held in place by the combined gravity of everything in the system. Astronomers call it the invariable plane, and nearly every major object follows it. It is one of the most reliable features of our cosmic neighborhood. The Kuiper Belt should follow it too. And, for the most part, it does. Objects orbiting between 30 and 80 times the Earth to star distance behave exactly as expected. Their average orbital tilt lines up neatly with the rest of the solar system. Predictable, orderly, boring even. Everything where it should be, but go farther out, past 80 times that distance, and everything changes. A team of researchers recently studied the orbits of over 150 Kuiper Belt objects that sit far enough from Neptune to be free of its gravitational grip. These are the independent drifters of the outer solar system, orbiting on their own terms. The team calculated the average plane these objects orbit along. Close in, it matched the inner solar system perfectly, but between 80 and 200 times the Earth to star distance, the plane tilted by about 15 degrees. The flat record was suddenly warped. That might sound small, but in orbital mechanics, a 15-degree shift in the average plane of an entire region is enormous. It means something is physically warping the outer solar system, bending the disk, pulling objects off the expected path and onto a tilted one, and this warping only shows up in the most distant parts of the belt. Closer to Neptune, everything looks completely normal. The contrast is sharp and deeply unsettling. The team ran complex simulations on powerful computers. They tested different combinations of mass and distance to figure out what kind of object could create this effect. Could it be a cluster of small bodies working together? Unlikely. The warp is too clean, too consistent across a wide range of distances. A swarm of tiny objects would create a messy, uneven distortion that shifts and wobbles over time. This looked like the work of a single, heavy hand, pressing down on the edge of the disk with steady, persistent force. Their conclusion pointed to something between the mass of Mars and Earth, orbiting at a steep angle far from our star. An object with enough gravitational pull to tilt the plane of everything around it for billions of miles in every direction. But here is the catch. Nobody has ever seen this object. It is completely invisible to every telescope that has searched for it, every survey, every satellite, every camera we have ever pointed at the outer solar system came back with nothing. The warping is there, but the source is a ghost. So, how can they be so confident it exists? Because the math does not lie. The warp is real, the tilt is measurable, and every simulation that tried to reproduce the observed shape of the Kuiper Belt without a hidden mass failed. The only model that works requires something heavy, lurking somewhere in the frozen dark, bending our solar system from the outside in. And this was just one piece of the puzzle, because across the country, another team was building a case for the same kind of invisible world, and their version was even bigger, much bigger. In 2016, 2 astronomers at the California Institute of Technology made an announcement that sent shockwaves through the scientific world. Mike Brown and Konstantin Batygin published a paper in the Astronomical Journal claiming that a massive, unseen planet was hiding in the outer reaches of our solar system. They called it Planet 9, and the evidence they presented was strong enough to make the entire astronomy community pay attention. Brown already had a reputation. He was the man who helped kill Pluto. His discovery of Eris in 2005 was one of the key reasons the International Astronomical Union rewrote the rules of what counts as a planet. Now he was back, this time claiming something far more dramatic: a real planet, possibly bigger than Earth, orbiting far beyond Neptune, and completely invisible to every instrument we had ever built. Their evidence was math. Brown and Batygin built computer simulations of the outer solar system and tried to reproduce the strange orbital clustering that had been spotted among the most distant Kuiper Belt objects. They tested every possible explanation they could think of: passing stars that might have disturbed the orbits long ago, the gravity of the Milky Way itself pulling on the outer solar system, random chance producing an illusion of order where none existed. None of them worked. Every alternative fell apart under scrutiny. The only scenario that matched what they were seeing required a planet, one with 5 to 10 times the mass of Earth, orbiting our star on a long, stretched-out path far beyond Neptune. Its orbit would be anti-aligned with the objects it was influencing, meaning its closest point to our star sits on the opposite side of the sky from theirs. This gravitational tug-of-war is what keeps those distant icy bodies locked in their strange formation over billions of years. The planet pulls them in one direction, and they settle into a pattern that mirrors its path. But Brown and Batygin did not stop there. Their model also predicted something nobody had expected. It said there should be objects in the Kuiper Belt that orbit at right angles to the rest of the solar system, tilted almost perpendicular to the plane all the other planets follow. When they checked the existing data, they found exactly that. Several known objects fit this prediction perfectly. They had been sitting in the catalogues for years, waiting for someone to explain why they followed such extreme paths. That was a powerful moment. Predicting something before you find it is one of the strongest tools in science. It meant their model was generating new, testable predictions, and those predictions were coming true with real data that anyone could verify. The scientific community took notice. Suddenly, the outer solar system was front-page news around the world. Still, there was one glaring problem that nobody could ignore. Despite years of searching with some of the most advanced instruments on Earth and in orbit, Planet 9 remained invisible. And that opened the door to skeptics, rival theories, and one very different idea about what might be hiding out there instead. The planet left clues everywhere it touched, but catching it on camera was proving to be an entirely different kind of challenge, one that would push technology to its absolute limits. You do not always need to see something to know it is there. Gravity does not care if you can photograph it. It pulls on everything around it, regardless, silently and constantly. And in the outer solar system, something is pulling hard, something that leaves marks on every object it touches. The case for a hidden planet does not rest on one piece of evidence. It rests on a pattern, a collection of gravitational effects that all point in the same direction, discovered by different teams using different methods at different times. Astronomers call this a gravitational fingerprint, and the one left by this unseen object is showing up everywhere they look. Every new dataset adds another layer to the case, and every layer makes the fingerprint harder to dismiss. First, there is the orbital clustering. A group of the most distant known objects in the Kuiper Belt share similar orbits, aligned in a way that random chance cannot explain. These objects are spread across enormous distances, separated by billions of miles of empty space, yet they all tilt and point in the same general direction. Without an outside force holding them in place, their orbits should have scrambled apart billions of years ago. The fact that they have stayed aligned is itself a mystery that demands a powerful answer. Then there is the warped plane. The flat disk of the outer Kuiper Belt bends at a sharp angle once you get far enough from Neptune. That warp requires a heavy, unseen mass pulling from a specific direction. Small objects working together cannot do that on their own. The distortion is too uniform, too persistent across billions of years of cosmic time. Next, there are the perpendicular orbits. Brown and Batygin's simulations predicted that a hidden planet would also push some objects into orbits at nearly right angles to the rest of the solar system. Sure enough, at least 5 known objects follow these extreme paths. They were discovered independently, long before anyone predicted they should exist. The fact that the theory explains objects found years earlier by unrelated research teams gives it a special kind of credibility that is hard to argue with. And then there are the Sednoids, objects like Sedna that orbit so far from Neptune that the ice giant's gravity cannot explain their paths. Something else had to place them on those long, lonely loops around our star, something with enough mass to reach across billions of miles and leave its mark on everything nearby. Their orbits are too extreme, too far from any known influence to have happened by accident. Each of these clues alone could be debated. Maybe the clustering is an observation bias. Maybe the warp has another cause. But together, they form a web of evidence that keeps pointing to the same answer. A large, unseen body hiding somewhere in the frozen outskirts, shaping orbits like a puppeteer behind a curtain. Pull on one thread and another tightens. That is what makes this evidence so compelling. It all connects. The fingerprint is clear. The question is whether we can match it to a face. And that hunt is turning into one of the biggest challenges in modern astronomy. How big is this thing supposed to be? The answer depends on who you ask, and the estimates keep shifting with every new study that comes out. When Brown and Batygin first proposed Planet 9 in 2016, they estimated it carried between 5 and 10 times the mass of Earth. That would make it a so-called super-Earth, or possibly a mini-Neptune. A world large enough to hold a thick atmosphere, maybe even wrapped in layers of hydrogen and helium gas, drifting in permanent cold, far from any warmth. A frozen giant with no starlight warming its surface. That estimate came from their simulations. They tested different sizes and distances, running the models over and over until the behavior of the outer Kuiper Belt matched reality. 5 to 10 Earth masses was the sweet spot. Anything smaller did not generate enough gravitational pull to herd the orbits. Anything bigger would have been spotted by existing telescopes. But in 2025, a new round of simulations refined the number. Researcher Amir Siraj and his colleagues at Princeton modelled the warped plane of the Kuiper Belt and tested how different-sized planets could reproduce the tilt. Their result landed at around 4.5 Earth masses, still enormous, still more than enough to dominate the outer solar system, but notably smaller than the original estimate. The planet was shrinking on paper, yet its influence remained staggering. To put that in perspective, Earth weighs about 13,000 trillion pounds. Multiply that by 4.5. That is the kind of mass we are talking about. A world heavy enough to bend the paths of thousands of icy objects across billions of miles. Heavy enough to reshape the edge of our solar system without ever being seen by a single camera. If it is a rocky world, like a scaled-up version of Earth, it could be around 2 to 3 times our planet's width. If it has a thick, gaseous envelope, it could be even larger, maybe 3 to 4 times Earth's diameter. Either way, it would be the kind of object that, under normal circumstances, should be easy to find. Planets this size show up around other stars all the time. We have catalogued thousands of them, orbiting distant stars across the galaxy. But this one is in our own backyard, and somehow it is still hiding. The reason comes down to distance. At hundreds of times the Earth to star separation, starlight reaching the planet is almost non-existent. The light that does arrive reflects off its surface at a fraction of its original strength. By the time that reflection travels back to Earth, it is so faint it vanishes into the background noise of the sky. It drowns in a sea of stars. That is the cruel math of the outer solar system. The bigger and farther an object is, the harder it becomes to detect. And this one sits at the extreme edge of both categories. So if we cannot see it, how do we narrow down where it is? That question has consumed the careers of dozens of astronomers, and the search has proven far more frustrating than anyone imagined. Every planet in our solar system follows a loop around our star. Earth takes 1 year, Jupiter takes about 12, Neptune, the farthest known planet, takes 165 years. That means Neptune has not even completed a single full orbit since it was discovered in 1846. It has only covered about 2/3 of its path in that time. Now, imagine a planet so far out that its orbit takes 10,000 to 20,000 years. That is the estimated range for Planet 9. One single trip around our star would stretch from the time ancient humans were painting cave walls all the way to today, and it would still not be done. Entire civilizations would rise and fall in the time it takes this world to complete a single lap. This is a major problem for detection. An object moving that slowly across the sky is almost impossible to spot through motion alone. Most planet searches work by looking for something that shifts position from night to night. But at Planet 9's distance, it might move less than the width of a single pixel on a telescope's camera over the course of an entire year. It is practically frozen against the background stars. The orbit is also extremely stretched out. It follows a long, narrow ellipse. At its closest approach to our star, it might come within 200 times the Earth to star distance. At its farthest, it could reach over 1,000. That means, for most of its orbit, it is even more distant and even dimmer than its average position suggests. There are long centuries where it drifts through the darkest, coldest stretches of the solar system, reflecting almost nothing. Scientists have tried to narrow down where along this massive loop the planet might be right now. Using the alignment of the Kuiper Belt objects it is supposedly influencing, they have ruled out large sections of the sky, but the remaining search area is still enormous. We are talking about scanning a region of space that covers a significant portion of the night sky, looking for a dot that might be fainter than a candle seen from 10,000 miles away. In 2021, Brown and Batygin refined their orbital estimate and shrank the predicted distance to around 380 times the Earth to star separation. Then they updated it again to around 460, and in 2025, another team pushed it down to roughly 290. The estimates keep changing, which tells us one important thing. We are still guessing. Every update narrows the field, but the target keeps moving. We are getting closer. The orbit is shrinking with every new piece of data, and a new telescope is about to change the entire game. Before we get there though, we need to talk about why nobody has found it yet, because the answer is more frustrating than you might expect. Decade after decade, the searches come back empty. Over the past decade, some of the most powerful telescopes ever built have scanned the outer solar system looking for Planet 9. Infrared satellites, wide-field survey cameras, deep space observatories. All of them came up empty. The most searched for object in modern astronomy remains completely invisible. The first major attempt used data from NASA's Wide Field Infrared Survey Explorer. This space telescope mapped the entire sky in infrared light, which is perfect for detecting warm objects glowing faintly in the dark. If a large planet existed out there, its residual internal heat should produce an infrared signature that stands out against the cold backdrop of space. The telescope searched the entire sky. It found nothing that matched the predicted signal. But that did not rule Planet 9 out. At the predicted distance, even the heat signature of a planet several times Earth's mass would be incredibly faint. The telescope was designed to find brown dwarfs and nearby stars, objects far brighter than an ice-cold super-Earth lurking at the edge of the solar system. The signal would be right at the limit of detection, buried in noise from every direction. The Pan-STARRS survey tried next. This ground-based system photographs the sky repeatedly, looking for anything that moves. It has discovered thousands of asteroids and comets, but Planet 9 moves so slowly that it would barely shift from one image to the next. Picking it out from billions of stationary stars is like finding a specific grain of sand on a beach, except the grain looks almost identical to every other grain around it. The task is nearly impossible with current methods. Other teams tried combining old data from different eras. One group in Taiwan compared infrared images from 2 space telescopes launched 23 years apart, hoping to spot something that moved between the 2 surveys. They found one promising candidate in the constellation Eridanus. But 2 faint dots across 2 decades of data are far from a confirmed planet. Follow-up observations are needed, and even the researchers admit the detection might be a false alarm caused by background noise. Part of the problem is the sky itself. The region where Planet 9 is predicted to orbit passes through parts of the Milky Way, where the background is dense with stars and glowing gas. Searching for a cold, dim object in front of that mess is like trying to spot a dark rock in a snowstorm at midnight. The background actively fights against you, and there is another layer of difficulty that makes everything harder. We do not know what we are looking for. Is it rocky or gassy? Does it have an atmosphere that reflects light, or a dark surface that absorbs it? These unknowns change what instruments you need and what signals you look for. Every wrong assumption wastes years of valuable telescope time. So the search continues with no clear end in sight. And while Planet 9 remains hidden, a completely different team proposed something surprising. Maybe the answer is 2 planets, not 1. In 2025, a team from Princeton University published a study that shook up the Planet 9 debate. Researcher Amir Siraj and his colleagues were not looking for Planet 9 at all. They were doing something simpler. They wanted to know if the Kuiper Belt was flat. The expectation was straightforward. The planets of our solar system orbit along a relatively flat plane. The Kuiper Belt, as an extension of the same disk, should follow a similar alignment. Siraj's team gathered data on over 150 Kuiper Belt objects and calculated their average orbital plane at different distances from our star. It should have been a routine measurement. Close to Neptune, the results matched perfectly. The belt was flat, aligned with the rest of the solar system, just as predicted. But beyond 80 times the Earth to star distance, the data shifted. The plane tilted. By about 15 degrees, something was pulling on the most distant objects, warping the shape of the belt in a way that could not be explained by any known planet or force. Siraj and his team ran simulations. They tested different combinations of mass, distance, and orbital angle to see what kind of object could produce this warp. The answer that kept coming back was a planet. But it was different from Planet 9. This one was closer to us, smaller, and orbiting at a distance of about 100 to 200 times the Earth. To star separation, the warp pointed directly at its hiding spot. They estimated its mass at 25 to 450 times that of Pluto. In more familiar terms, that puts it somewhere between the mass of Mercury and Earth, a real world with serious gravitational influence. To distinguish it from Planet 9, the team gave it a new name, Planet Y, The reaction from the scientific community was mixed. Some astronomers found the evidence compelling. One researcher who had independently studied the warped plane of the Kuiper Belt agreed that a body in this mass range was plausible and consistent with the data. Others were more cautious, pointing out that the dataset of distant Kuiper Belt objects is still small, and observational biases could be skewing the results in misleading ways. But the most exciting part of the Planet Y hypothesis is what it does not do. It does not replace Planet 9. The two theories address entirely different problems. Planet 9 explains the clustering of extreme orbits far out in the scattered disk. Planet Y explains the warped plane of the mid-range Kuiper Belt. They could both be wrong, or they could both be right. The two mysteries exist independently of each other, and if both are real, that means our solar system has two undiscovered worlds waiting in the cold. That possibility alone is enough to keep every telescope on Earth pointed at the outer darkness. But could two hidden planets really coexist in the same solar system without us knowing? The science says yes, and the reasons are cleaner than you might think. The idea that our solar system could be hiding two undiscovered planets sounds extreme, but the science behind it is surprisingly clean. The math works, the orbits do not collide, and the evidence points in two completely different directions. Planet 9 and Planet Y are answers to different questions. Planet 9 was proposed to explain why a handful of the most distant objects in the solar system share eerily similar, clustered orbits. These objects sit far out in the scattered disk, well beyond the main Kuiper Belt, at distances of 250 or more times the Earth to star separation. Something massive and distant, with 5 to 10 Earth masses, would be needed to keep them locked in alignment over billions of years. Planet Y addresses a completely different puzzle. The average orbital plane of mid-range Kuiper Belt objects, those between 80 and 200 times the Earth to star distance, tilts away from the expected alignment by about 15 degrees. A planet the size of Mercury to Earth, orbiting closer than Planet 9, could produce exactly that kind of warp. Different distance, different mass, different effect on different objects. The key is that these two effects show up at different distances and involve different groups of objects. Planet 9 works on the farthest scattered disk bodies. Planet Y affects the middle reaches of the belt. Their gravitational zones barely overlap. One does not cancel out the other. They operate in separate lanes of the outer solar system. Siraj, the lead researcher behind the Planet Y study, said it openly. Planet 9 and Planet Y could both exist. Both could be shaping the outer solar system in their own way, from their own orbits, without interfering with each other. Two invisible hands, working on two different sections of the same frozen frontier. If that is the case, the outer solar system is far more crowded and complex than anyone imagined. For decades, the region beyond Neptune was treated like an afterthought, a frozen wasteland with a few scattered ice chunks and nothing important happening. Now, it is looking more like a hidden neighborhood with major residents we have never met and forces we have never measured. Of course, there is a flip side. Both theories are based on indirect evidence, gravitational models, statistical patterns, simulations that depend on assumptions. No one has seen Planet 9 or Planet Y through a telescope, and until someone does, skeptics will argue that maybe these patterns have simpler explanations that do not require invisible worlds. Some researchers believe the orbital clustering is just an observation bias created by uneven telescope coverage. Others think the warped plane could be a relic of the early solar system, a frozen imprint from some ancient event that no longer has an active cause behind it. But the teams behind both hypotheses are confident that the patterns are real, and a new wave of telescopes is about to settle the debate one way or the other. Before that, though, we need to talk about some of the strangest objects ever found at the edge of our solar system, because they add yet another layer to this growing mystery, and they might be the most important clue of all. In 2003, astronomer Mike Brown and his team discovered an object so far from our star that it redefined what we thought the solar system looked like. They named it Sedna, after an Inuit goddess who lives at the bottom of the freezing Arctic Ocean. The name fit perfectly. Sedna orbits our star on an incredibly stretched out path. At its closest, it comes within about 76 times the Earth to star distance. At its farthest, it swings out to nearly 900. One full orbit takes over 10,000 years. Sedna never enters the main Kuiper Belt. It never gets close enough to Neptune for the ice giant to influence its path. It is completely detached, drifting through a region of space that, by all existing models, should be empty. That was the first problem. How did Sedna get there? Objects do not just appear on extreme orbits. Something had to push it. A passing star, a rogue planet, or a massive body still hiding in the outer solar system. At the time, nobody knew the answer. Sedna just sat there, circling in silence, demanding an explanation that nobody could give. Then came more discoveries. In 2014, another object called 2012 VP 113 was found on a similarly extreme orbit. Same general characteristics. Far from Neptune, detached from the known planetary influences, and its orbit was aligned with Sedna's in a way that seemed unlikely to be a coincidence. Astronomers started calling these objects Sednoids, extreme trans-Neptunian objects on long, lonely paths that no known planet could explain. For years, only 2 were confirmed. Finding them is incredibly hard because they spend most of their orbits in the darkest, most distant corners of the solar system, too faint to detect. Then, in 2025, a team using Japan's Subaru telescope in Hawaii announced the 4th Sednoid ever found. They nicknamed it Ammonite, after the ancient spiral-shelled creature, and it threw a wrench into everything scientists thought they understood about the outer solar system. Ammonite's orbit is different. Its closest point to our star faces the opposite direction from the other 3 Sednoids. If a single hidden planet like Planet 9 was herding all these objects into aligned paths, Ammonite should follow the same pattern. It does not. It goes its own way, as if responding to a completely different set of rules. That discovery did 2 things at once. It weakened the simplest version of the Planet 9 theory, because Ammonite does not fit the predicted clustering, but it also strengthened the case that something complex is happening out there. If one planet cannot explain all 4 Sednoids, maybe the outer solar system is even messier than we thought. Maybe multiple forces are at play. Maybe there was once a planet that got ejected long ago, leaving behind a trail of scattered objects with no shepherd. Whatever the answer is, the Sednoids are telling us that the edge of our solar system is anything but empty. It is a graveyard of clues, each one pointing deeper into the dark. And the deeper we look, the stranger the landscape becomes, because just past the Kuiper Belt there is a cliff, and on the other side, everything vanishes. If you map the number of objects in the Kuiper Belt by distance, a clear pattern emerges. Close to Neptune, the belt is crowded. Thousands of icy bodies orbit in tight loops, pushed and pulled by the ice giant's gravity. As you move outward, the population stays healthy, stretching across billions of miles of frozen space. Then, at around 50 times the Earth to star distance, the population drops off a cliff. A sudden, sharp plunge. The number of large objects falls to almost nothing. Astronomers call this the Kuiper Cliff, and nobody can fully explain it. This is strange because models of the early solar system predict the opposite. When the planets were forming, the disk of gas and dust that gave birth to everything should have extended well past this point. There should be plenty of material out there, enough to build objects hundreds of miles wide. Instead, there is a wall of emptiness. The construction material vanished, and nobody knows where it went. Several explanations have been proposed. One idea is that the material beyond 50 times the Earth to star distance was simply too spread out. The building blocks were there, but they were too far apart to collide and stick together into larger objects. Gravity needs density to work, and out there, the density may have been too low to build anything significant. Another theory suggests that something swept the region clean, a large body moving through the area early in the solar system's history could have scattered or absorbed the material that should have been there. If a planet once existed in this region and later got kicked out by a gravitational encounter, it might have taken most of the debris with it or flung it into wildly different orbits on its way out. A third possibility is even more unsettling. Maybe the objects are still there, and we simply cannot see them. At those distances, even large bodies reflect so little starlight that they vanish from our instruments. The cliff might be a limit of our technology rather than a real feature of the solar system. We could be staring right at a populated region and seeing nothing. But recent discoveries are poking holes in the cliff theory. NASA's New Horizons team, using the powerful Subaru telescope in Hawaii, found objects stretching out to nearly 90 times the Earth to star distance. That is well past the supposed cliff. These objects should not be there according to older models. Yet, there they are. Faint, distant, and very much real. That finding opened up a possibility that stunned the astronomy community. What if the Kuiper Belt does not end at all? What if it keeps going, far past the boundary we assumed? Or what if there is a second belt out there, hiding behind the cliff, filled with objects we have never counted? The edge of the solar system is clearly not where we thought it was, and the farther we push, the more questions pile up, including one that nobody expected. What if the belt itself has a hidden structure inside it that we have been overlooking this entire time? For decades, the Kuiper Belt was treated as a single region, a wide ring of icy debris starting at Neptune's orbit and fading out around 50 times the Earth to star distance. Clean, simple, done. Case closed. Then, the New Horizons mission changed everything. New Horizons launched in 2006 with one primary goal: fly past Pluto and send back the first close-up images of the dwarf planet. It did that brilliantly in 2015, revealing a world far more complex and active than anyone predicted. Mountains of water ice, glaciers of frozen nitrogen, a thin atmosphere clinging to a surface that should have been dead billions of years ago. But Pluto was not the end of the mission. After the flyby, New Horizons kept going, deeper into the Kuiper Belt. In 2019, it flew past a small object called Arakoth, a snowman-shaped body made of two fused lobes. It was the most distant object ever visited by a spacecraft, and it told scientists that the Kuiper Belt was more complex than they had imagined. Then came the real surprise. The New Horizons science team, working with the Subaru telescope, began detecting objects far beyond the expected edge of the belt. These were not scattered, random strays. They formed a population, a group of icy bodies clustered between 70 and 90 times the Earth to star distance, well past the Kuiper Cliff that was supposed to mark the end of everything. Every model of the solar system said the belt should thin out and disappear by 50 times the Earth to star distance. Finding a substantial population of objects nearly twice that far out meant one of two things. Either the Kuiper Belt is far larger than we believed, stretching much deeper into space, or there is a second, distinct belt sitting beyond the first one, separated by the cliff, like two rings around a target. One researcher on the team pointed out that if this result holds up, our Kuiper Belt might match those around other stars after all. For years, astronomers noticed that the debris disks around distant stars were much larger than ours appeared to be. That gap always seemed odd. Maybe our belt looked small only because we had not searched deep enough. The implications ripple outward. If the Kuiper Belt extends farther or doubles, then the total mass of the outer solar system is much greater than current estimates. That extra mass changes models of how the solar system formed. It changes predictions about what kinds of objects exist out there. And it makes the case for hidden planets even stronger, because more material means more gravitational complexity and more places for a planet to hide. New Horizons is still out there right now, roughly 60 times the Earth to star distance from our star, cruising through the very region these new objects were found. It is running low on power, but still sending data home, and every bit of information it beams back rewrites what we thought we knew about the boundaries of our solar system. But the outer belt was not done surprising us, because inside the main Kuiper Belt itself, a team of researchers found something hidden in plain sight, a structure nobody had noticed in decades of observation. Sometimes, the biggest discoveries come from seeing old data in a new way. A team of researchers from Princeton University and the Institute for Advanced Study decided to look at the Kuiper Belt with fresh eyes. They took a database of over 1,600 classical Kuiper Belt objects, the well-behaved ones with stable orbits, and ran them through an algorithm that had never been used on this region before. The algorithm was called DB-Scan. It was originally designed to find clusters in massive astronomical datasets, like identifying groups of stars buried in the data from the Gaia Space Telescope. The idea was simple. Feed it a cloud of data points and let it find neighborhoods, dense clusters that stand out from the surrounding noise. Let the math reveal what human eyes cannot. Before they could use it, the team had to do something clever. The raw orbits of Kuiper Belt objects change over time because Neptune's gravity constantly tugs on them. So instead of using the current positions, the researchers calculated what each orbit would look like without Neptune's influence. They stripped away the giant planet's fingerprint and revealed the true underlying structure that had been hidden beneath layers of gravitational distortion. Then they ran the algorithm, and it found something nobody had noticed before. Sitting right next to a well-known cluster of objects called the core, the algorithm identified a second group, tighter, more circular, calmer. The team named it the inner core. It was a distinct population of Kuiper Belt objects whose orbits were so orderly, so undisturbed, that they appeared to have been sitting in the same place since the earliest days of the solar system. 4.5 billion years of quiet drifting in one small corner of the belt. The inner core objects had noticeably lower eccentricity than their neighbors in the regular core. That meant their orbits were closer to perfect circles. In orbital mechanics, circular orbits suggest a region that has been left alone. No violent collisions, no gravitational bullies shoving things around, just silence and stability stretching back to the birth of the planets. The researchers could not say for certain whether the inner core was a separate structure or just an extension of the known core that had been overlooked for decades. But either way, its existence meant the Kuiper Belt is more organized than anyone assumed. It has layers, neighborhoods, zones with different histories and different levels of disturbance, sitting side by side in the frozen dark. This discovery matters because it challenges the idea that the outer solar system is a simple, messy junkyard. It has architecture, and if there is hidden structure in the belt, that structure could hold clues about what forces shaped it over the ages, including, possibly, the gravitational influence of a hidden planet that passed through long ago or still orbits nearby today. Every time we look at the Kuiper Belt with better tools, we find something new. But to understand why the belt looks the way it does, we need to talk about the force that shaped most of it, the gravitational bully that controls the gate between the known solar system and the outer frontier. Neptune does not get the attention it deserves. It is the most distant known planet, a cold blue giant sitting about 30 times the Earth to star distance from the center of our solar system. It takes 165 years to complete a single orbit. Most people forget it exists entirely. But in the outer solar system, Neptune is king, and it rules with a heavy hand. Its gravitational reach is enormous. Neptune shapes the inner edge of the Kuiper Belt, like a potter shaping clay on a spinning wheel. Objects that drift too close get locked into orbital patterns called resonances, where their orbit period becomes a neat fraction of Neptune's. Pluto, for example, completes 2 orbits for every 3 that Neptune makes. This is called a 3-to-2 resonance, and it is the only reason Pluto's orbit is stable. Without it, Neptune would have flung Pluto out of the solar system long ago. Hundreds of Kuiper Belt objects share similar resonances with Neptune. Some follow a 4-to-3 pattern. Others are locked in 5-to-3 or 2-to-1. These relationships are the result of Neptune's migration billions of years ago, when the ice giant drifted outward from its original position closer to our star and bulldozed through the primordial disk of debris. It was a slow-motion wrecking ball that reshaped everything in its path. That migration was violent. As Neptune pushed outward, it scattered everything around it. Some objects were flung inward, becoming centaurs, icy bodies orbiting between Jupiter and Saturn on borrowed time. Others were launched outward into the scattered disk, a chaotic region of objects on wildly elongated orbits that stretch far from our star. And some were captured into resonances, trapped in Neptune's gravitational rhythm forever, locked in a dance they can never leave. The objects that survived this chaos and settled into stable, calm orbits became the classical Kuiper Belt. These are the well-behaved citizens of the outer solar system. They orbit between about 42 and 48 times the Earth-to-star distance, mostly unbothered by Neptune's influence. They are the frozen leftovers that Neptune did not manage to scatter or swallow during its rampage. But Neptune's power has limits. Beyond about 50 to 80 times the Earth-to-star distance, its gravitational grip fades to almost nothing. Objects out there are free agents. They orbit under the influence of the overall mass of the solar system, plus whatever else might be lurking in the dark. And it is in this region, beyond Neptune's reach, that all the strange patterns show up. The clustered orbits, the warped plane, the Sednoids on impossible paths that nothing in our current understanding can explain. Neptune cannot explain any of it. It is too far away. Its gravity is too weak at those distances to hurt anything. Whatever is causing the disturbances in the deep Kuiper Belt has to be something else entirely. Something that operates beyond Neptune's territory, in a zone that no known planet controls. That gap in control is exactly where the mystery lives. And it is exactly where some scientists think we should stop looking for planets altogether. Because maybe the answer is simpler than we think. Some respected astronomers think the whole idea of hidden planets is a mirage, an illusion created by the way we look at the sky. The strongest version of this argument centers on observation bias. Telescopes cannot see the entire sky at once. They point at specific patches, often the same patches over and over, because that is where existing surveys are aimed. If you only search certain areas, you will only find objects in those areas. And if the objects you find happen to line up, it might be because you never looked anywhere else. The clustering could be an artifact of incomplete coverage rather than evidence of a hidden world. This criticism is taken seriously. Several independent studies have tried to determine whether the orbital clustering of distant Kuiper Belt objects is real or a statistical shadow of uneven sky coverage. The results are mixed. Some analyses say the clustering holds up even after correcting for bias. Others say it weakens or disappears entirely. The debate is ongoing, and neither side has delivered a knockout blow. There is also the self-gravity argument. The Kuiper Belt contains a huge amount of mass, scattered across trillions of cubic miles of space. Individually, these objects are tiny, but collectively, their gravity adds up. Some researchers have proposed that the combined pool of thousands of small icy bodies could mimic the effect of a single large planet. Under the right conditions, Their collective gravity could shepherd orbits into alignment without needing a massive hidden world pulling from the shadows. This idea is harder to test. Modeling the gravitational interactions of thousands of small objects over billions of years requires enormous computing power and a lot of assumptions about how many objects exist and where they are. Current estimates suggest the total mass of the Kuiper Belt is only about 1/10 of Earth's mass, which seems too low to produce the observed effects. But if the belt extends farther than we think, or if the second population discovered by New Horizons adds significant mass, the numbers could change dramatically. Then there is the simplest argument of all. Maybe we just do not have enough data yet. The sample of extreme trans-Neptunian objects is still small. Fewer than a few dozen are known. Drawing conclusions about a hidden planet from such a limited dataset is risky. Every new discovery could shift the statistics dramatically. Ammonite already showed how a single object can shake the entire framework overnight. Critics also point to the long history of failed planet predictions. For over a century, astronomers searched for a planet X beyond Neptune, convinced that gravitational anomalies required a hidden world. Pluto was found during that search, but it turned out to be far too small to explain the anomalies. Later, better measurements of Neptune's mass showed the anomalies were never real in the first place. It was a ghost chase, built on bad data. Could Planet 9 be the same kind of mistake? It is possible, but there is a key difference. The evidence this time comes from multiple independent lines of reasoning, working with different datasets, arriving at the same conclusion. And until a better explanation emerges, the planet hypothesis remains the leading candidate. The debate is healthy. Science works best when ideas are challenged hard, and the ultimate judge will be a telescope, not an argument. But before we get to that telescope, there is one more origin story worth telling. Because if a hidden planet does exist, it had to come from somewhere, and the possibilities are wilder than you might expect. If Planet 9 is real, where did it come from? A planet that massive, sitting that far from our star, does not fit neatly into any standard model of how solar systems form. Its existence demands an origin story, and every option on the table is stranger than the last. One theory says it was born close to our star, in the same crowded disk of gas and dust that created Jupiter, Saturn, Uranus, and Neptune. During the chaotic early era of the solar system, gravitational encounters between the young giant planets could have flung one sibling outward. The ejected world would have travelled far, but stayed tethered to our star's gravity by the thinnest thread, a banished family member still orbiting the home it was kicked out of. This idea has support from simulations. A 2025 study, published in Nature Astronomy, showed that during the early phase of planetary formation, when the young solar system was still embedded in a cluster of other newborn stars, gravitational chaos was the norm. Planets got scattered constantly. Some were ejected completely, becoming rogue planets that drift through the galaxy with no star at all. But others were lucky. They got kicked far enough to reach the outer solar system, then captured into stable orbits by the combined gravity of everything left behind. The simulations found that there is roughly a 40% chance a Planet 9 type object could have been trapped during this messy period. That is surprisingly high for something that has never been directly observed. A second theory flips the script entirely. What if Planet 9 did not form here at all? What if it was stolen from another star? In the first few 100 million years of the solar system, our star was surrounded by dozens or even hundreds of sibling stars, all born from the same molecular cloud. These stars were close together, close enough for their gravitational fields to overlap. In that environment, planets could be pulled from one star's orbit and captured by another during a close flyby. If a neighbouring star had a planet on a wide orbit, our star could have grabbed it as the two stars passed each other. The stolen planet would settle into a distant, tilted orbit, a cosmic immigrant, born around an alien star and adopted by ours billions of years ago. A third possibility is the darkest of all. Planet 9 could be a rogue planet that was wandering through interstellar space and just happened to pass close enough to our star to be captured. Rogue planets are surprisingly common. Astronomers estimate there could be billions of them drifting through the Milky Way, untethered to any star. Most pass through solar systems without stopping, but every now and then the geometry and speed line up just right, and a wanderer gets caught in a gravitational net. Each of these origins would leave different signatures on the planet's composition, orbit, and influence on the surrounding Kuiper Belt. If we ever find it, studying its properties could tell us where it came from. And that story could rewrite the history of our entire solar system. But origin stories only matter if the planet is real. And to find out, we need to look past the Kuiper Belt itself, into a region so vast and so dark that even light takes days to cross it. Beyond the Kuiper Belt, beyond the scattered disk, beyond every known object in our solar system, there is a place so remote that no telescope has ever directly seen it. It is called the Oort Cloud, and it is the true boundary of our star's kingdom. The Oort Cloud is not a belt or a ring, it is a shell, a massive hollow sphere of trillions of icy objects, wrapping around the entire solar system like a cocoon. It begins at roughly 2,000 times the Earth to star distance and stretches out to 100,000. At its outer edge, the gravitational pull of our star is so weak that a passing star or the tidal pull of the Milky Way itself can dislodge objects and send them tumbling inward toward the planets. That is exactly what happens. Every long-period comet that streaks through the inner solar system, the kind that appears once and never comes back within a human lifetime, is believed to have started in the Oort Cloud. Something nudged it loose from its ancient orbit, and it fell toward our star, picking up speed and brightness as it heated up, before swinging back out into the dark for thousands of years. The Oort Cloud was first proposed in 1950 by Dutch astronomer Jan Oort. He noticed that long-period comets arrive from all directions, not along the flat plane of the planets. That meant their source had to be spherical. His calculations suggested a vast reservoir of icy bodies surrounding the solar system at enormous distances. The idea has held up for over 70 years, even though no one has ever directly observed a single Oort Cloud object sitting in place. We know it is there because of the comets. They keep coming, generation after generation, and the math tells us that the inner solar system destroys comets faster than the Kuiper Belt alone can replace them. There has to be another, larger reservoir feeding the supply. That reservoir is the Oort Cloud. Scientists estimate it contains somewhere between 1 trillion and 10 trillion icy objects. The total mass could be significant, though estimates vary widely. These objects are tiny and incredibly faint. Even a body the size of a mountain would be invisible at those distances. There is no telescope on Earth or in orbit that can spot them where they live. The objects in the Oort Cloud did not form there. They were born much closer to our star in the region around Uranus and Neptune. During the violent early years of the solar system, gravitational interactions with the giant planets flung them outward, far enough to reach the edges of the star's gravitational influence. Some escaped entirely and became rogue bodies drifting through the galaxy. The rest settled into the Oort Cloud, where they have been circling in near-perfect silence for over 4 billion years. The cloud has 2 layers. A flattened inner region called the Hills Cloud, which is somewhat aligned with the rest of the solar system, and a spherical outer region that wraps around everything like an enormous bubble. The inner cloud is more densely packed. The outer cloud is thin, spread across an almost unimaginable volume of space. If the Kuiper Belt is the porch of our solar system, the Oort Cloud is the fence at the edge of the property. And somewhere between the two, in the vast no-man's land of the outer solar system, a hidden world might be circling in silence. Finding it will take a machine unlike anything we have built before. and that machine is almost ready to open its eyes. High on a mountaintop in the Chilean Andes, a telescope is about to change everything we know about the outer solar system. It is called the Vera C, Rubin Observatory, and it was built for exactly this kind of hunt. The observatory is named after the legendary astronomer Vera Rubin, who spent her career studying how galaxies rotate and helped uncover some of the strongest evidence for dark matter. Her work proved that the universe contains far more than what we can see. Now her namesake telescope is designed to do something similar, reveal what is hidden in the darkest corners of our own solar system. The Rubin Observatory houses the largest digital camera ever constructed. It is roughly the size of a small car and contains over 3 billion pixels. Every few nights, it will photograph the entire visible southern sky, building a moving picture of the universe that updates in near real time. Over its planned 10-year survey, it will catalogue billions of stars, galaxies, asteroids, and anything else that moves or changes across the sky. For the search for Planet 9 and Planet Y, this is a game changer. The observatory's enormous field of view means it does not have to guess where to look. It photographs everything. If a faint, slow-moving object is drifting through the outer solar system, the Rubin Observatory will see it shift from image to image over weeks and months. That kind of systematic, unbiased coverage is exactly what previous searches have lacked. No more pointing at patches of sky and hoping for the best. The telescope can also see incredibly faint objects. Its mirror system gathers light from sources that are far dimmer than what most ground-based telescopes can detect. A planet several times the mass of Earth, reflecting a tiny sliver of starlight from hundreds of times the Earth to star distance, should fall within its detection range. If Planet 9 exists anywhere in the predicted search zone, Rubin has a realistic shot at catching it on camera. But even if the planet itself remains invisible, the observatory will transform the debate in another way. It is expected to discover thousands of new Kuiper Belt objects, many of them in the distant reaches where the strange orbital patterns show up. With a much larger sample of objects, scientists can test whether the clustering is real or a product of bias. They can measure the warped plane with far greater precision, and they can find new sednoids that either support or undermine the planet hypothesis with fresh data. Some astronomers believe that Rubin will settle the question within its first few years of operation. Others think the answer will come more slowly, through the gradual accumulation of data that narrows the possibilities until only one explanation remains standing. Either way, the era of guessing is almost over. A machine built to find what is hidden is about to stare into the deepest, darkest corners of our solar system, with eyes sharper than anything that came before it. And whatever is out there will have nowhere left to hide. But the Rubin Observatory is not the only tool in the search. Another group of scientists decided to try a completely different strategy. Instead of looking for reflected light, they went hunting for something else entirely: heat. Most planet searches rely on reflected starlight. Light leaves our star, travels billions of miles to the outer solar system, bounces off a distant object, and then travels all the way back to a telescope on Earth. At Planet 9's predicted distance, that round trip leaves the signal unimaginably faint. It is like trying to spot a dark pebble by the glow of a candle placed a mile away in a dense fog. So a team of researchers in Taiwan decided to flip the approach entirely. Instead of looking for bounced light, they searched for the planet's own heat. Every large body in space emits some thermal radiation. Even a cold planet at the edge of the solar system still has residual internal heat from its formation, slowly leaking outward through its surface over billions of years. This heat glows in the far infrared, a part of the light spectrum that our eyes cannot see, but specialized telescopes can detect. The advantage is that this signal travels directly from the planet to us. No round trip, no bounce, just a straight line of warmth cutting through the dark. The team, led by graduate student Terry Long Fan and his advisor Tomotsugu Goto at National Tsinghua University used data from 2 infrared space telescopes launched over 2 decades apart. The first was the Infrared Astronomy Satellite, a joint mission launched by NASA, the Netherlands, and the United Kingdom in 1983. The second was Ikari, a Japanese satellite launched in 2006. The strategy was elegant. Planet 9 moves so slowly that over 23 years it would shift only slightly across the sky. By comparing images from both telescopes, the team looked for faint infrared sources that appeared to move between the 2 surveys by just the right amount to match the predicted motion of a distant planet. They started with roughly 2 million infrared sources. Then they removed everything that did not move, everything that moved too much, and everything contaminated by background noise. The list shrank from millions to thousands, then to hundreds, then to just 13 candidates. Most of those turned out to be false alarms caused by noise or background galaxies. But one stood out, a pair of faint dots in the constellation Eridanus that moved at a rate consistent with a distant, slow orbiting planet. The team published their finding, but they were careful with their language. 2 detections across 2 decades are far from enough to confirm a planet. The signal could be noise. It could be a background galaxy that happened to align with the predicted motion by pure coincidence. Follow-up observations with more powerful telescopes are needed before anyone can call it a discovery. The researchers themselves emphasize this uncertainty, but the approach itself is promising. If Planet 9 has even a small amount of internal heat, infrared telescopes may be the key to finding it, and as new, more sensitive infrared instruments come online in the years ahead, the chances of a detection go up. Still, even the best instruments need to know roughly where to point, and every new piece of data brings us a little closer to answering the biggest question in planetary science right now. What would finding this planet actually mean for our understanding of the universe? If a new planet is confirmed in the outer solar system, it would be one of the most significant astronomical events in nearly 2 centuries. And it would carry a poetic echo of a discovery made in 1846 that changed science forever. That year, astronomers found Neptune. They found it by math. French mathematician Urbain Le Verrier noticed that Uranus was not behaving the way it should. Its orbit wobbled in ways that could only be explained by the gravitational pull of an unseen planet farther out. Le Verrier calculated where that planet should be, pointed a telescope at those coordinates, and there it was, a pale blue dot, right where the numbers said it would be, waiting to be seen. It was the first time a planet had been predicted before it was observed. The discovery proved that gravity could reveal what light could not, and it cemented the idea that mathematical models could uncover hidden truths about the universe that no human eye had ever witnessed. Planet 9, if it is found, would follow the same script, almost beat for beat. Its existence has been predicted based on gravitational disturbances in the orbits of distant objects. Researchers have used computer simulations to estimate its mass, distance, and orbital path. All that remains is for a telescope to look in the right place and capture that faint pinprick of light against the vast black background of space. The parallels go even deeper. Just as the discovery of Neptune reshaped our understanding of the solar system in the 19th century, confirming Planet 9 would reshape it again today. It would mean the outer solar system is far more dynamic and populated than current models assume. It would force a revision of how we think about planetary formation across the galaxy, and it would raise immediate questions about what other worlds might be lurking in the dark spaces between stars that we have never thought to explore. For the scientific community, the impact would be enormous. Textbooks would need rewriting. Models of solar system architecture would need updating from the ground up, and the field of planetary science would gain a new frontier to explore, one that is right in our own backyard. Careers would be built around studying a world that, just a few years earlier, existed only as a set of equations on a whiteboard. But beyond the technical implications, there is something else, something more personal and deeply human. Finding a hidden planet in our own solar system would remind us that discovery is alive, that the age of exploration did not end with the last moon landing or the last rover on Mars. The universe still has secrets, and we are still capable of uncovering them when we look with enough patience and precision. That kind of moment does not come along often, and when it does, it changes more than science. It changes how we see ourselves and our place in the cosmos. But what would it actually mean beyond the headlines? How would this change our understanding of how solar systems form in the first place? The answer reaches far beyond our neighborhood. Finding a hidden planet beyond Neptune would crack open one of the deepest questions in astronomy. How do solar systems form, and how did ours end up looking the way it does? Right now, our best models of planetary formation say that the solar system grew from a spinning disk of gas and dust around 4.5 billion years ago. Close to our star, where the disk was hot and dense, rocky planets formed. Farther out, where temperatures dropped low enough for gases to clump together, the giant planets took shape. And beyond that, the leftover debris settled into the Kuiper Belt, and eventually the Oort Cloud. These models work well for the 8 known planets, but they struggle with the outer edges. The predicted amount of material beyond Neptune does not match what we observe. The Kuiper Belt appears to have far less mass than it should, given what simulations say was available during formation. Either something removed that mass over billions of years, or the original disk was shaped differently than we think. A hidden planet changes the equation entirely. If a world several times the mass of Earth has been orbiting in the outer solar system since the beginning, it means the disk of material that formed the planets extended much farther than current models assume. That extra reach could explain why the Kuiper Belt exists at all, and why it has the layered, complex structure that researchers keep uncovering. It could also explain the Kuiper Cliff. If a large planet formed in the region around 50 to 80 times the Earth to star distance, and then migrated outward over millions of years, it could have swept the zone clean on its way, creating the sharp drop-off we see today. The cliff would no longer be a mystery. It would be a scar left behind by a planet we never knew was there, carved into the architecture of the outer solar system. More broadly, confirming a distant planet in our solar system would change how we interpret the debris disks we see around other stars across the galaxy. Many of those disks are much larger and more massive than ours appears to be. If our belt actually extends farther than we thought, and if hidden planets are common in outer solar systems, then maybe planetary architectures across the galaxy are more similar than they seem. We might be more typical than we believed. This is also connected to the growing catalogue of rogue planets wandering through interstellar space. If the early solar system ejected one or more planets during its chaotic formation phase, those lost worlds are now drifting through the galaxy untethered. Every rogue planet tells the story of a solar system that could have looked different, and every hidden planet that stayed behind tells the story of one that almost got away, but did not. The answers are about more than our past. They are about the present and future of how we understand every planetary system in the universe. And the key to unlocking all of it might be sitting in the cold dark right now, a few hundred times the Earth to star distance away, waiting to be seen for the first time. But there is a bigger picture here, too. One that goes beyond science and into something more human. Something about who we are and what we are capable of. Step back for a moment. Forget the simulations. Forget the orbital math and the telescope specs. Think about what it means that we might not know our own solar system. We have mapped the surface of Mars down to the meter. We have sent robots to the moons of Saturn. We have photographed black holes 65 million light years away. And yet, right here, in the same system we were born in, there could be an entire planet that we have never seen, a world bigger than Earth, circling our star for billions of years, completely invisible to every instrument we have ever built. That is a reminder. The universe is nowhere close to finished showing us things. We are far less advanced in our understanding than we sometimes believe. Humans have a habit of thinking we have figured it all out. Every few decades, someone declares that the age of discovery is winding down, that all the big questions have been answered. And every time, the universe proves us wrong. The discovery of dark energy in 1998, the detection of gravitational waves in 2015, the first image of a black hole in 2019. Each of these moments came from places we were never expecting to look. A hidden planet in our solar system would join that list. It would say, clearly and unmistakably, that the closest frontier is still wild and unexplored, that you do not need to travel to another galaxy to find something unknown. You just need to look a little farther than you did yesterday. The edge of the familiar is where the surprises live. There is also something deeply humbling about it. We struggle to find a planet that might be larger than Earth, orbiting within the gravitational territory of our own star. Meanwhile, the observable universe contains an estimated 2 trillion galaxies, each holding hundreds of billions of stars, most of which have their own planets. The sheer scale of what we do not know is staggering. It is enough to make you dizzy if you sit with it long enough, and yet we keep looking. That is the part that matters most. Every telescope pointed at the sky, every algorithm sifting through data, every graduate student squinting at infrared images from decades-old satellites. All of it is a bet that the next answer is within reach. All of it is an act of faith in the process of discovery. If Planet 9 or Planet Y is found, it will spark years of new research. Missions will be proposed to visit it. Instruments will be designed to study it. Entire careers will form around understanding a world that, right now, exists only as a gravitational whisper in the orbits of distant ice. And if it is never found, that matters too. Ruling it out would tell us that the strange patterns in the outer solar system have a different cause, one we have not imagined yet. Either way, the search pushes us forward. Either way, we learn something about the universe and about ourselves. Science does not promise answers on a schedule, but it promises that if you keep asking, the answers eventually come. And right now, one of the biggest answers in all of astronomy might be hiding just beyond the reach of our best telescopes, circling in the dark, waiting for the moment we look in exactly the right place. The race to find it is already underway. Right now, multiple teams around the world are chasing the same prize. The first confirmed detection of a new planet in our solar system. It would be the discovery of a lifetime, the kind of moment that gets remembered for centuries. And the competition is fierce. Brown and Batygin at Caltech continue to refine their orbital models, narrowing the search zone with every new Kuiper Belt object that gets discovered. They have ruled out large portions of the sky, shrinking the haystack even as the needle remains hidden. Every few months, they publish updated predictions, adjusting the estimated mass, distance, and orbital shape based on the latest data from surveys around the world. Meanwhile, Siraj and his team at Princeton are pursuing the Planet Y hypothesis, using the warped plane of the Kuiper Belt to point toward a different kind of hidden world. Their approach targets a closer, smaller planet, one that could be detected sooner because it reflects more starlight than a more distant object would. If Planet Y is real, it might be the first one we actually photograph. In Taiwan, Fan and Goto are preparing follow-up observations for their infrared candidate. They need deeper images from more powerful telescopes to determine whether the pair of faint dots they found in Eridanus is a real moving object or a statistical ghost born from background noise. Confirmation could take months or even years of careful observation. And then there is the Vera Rubin Observatory. Once it begins its full sky survey, it will generate a flood of data unlike anything astronomy has seen before. Automated software will flag moving objects in real time. Astronomers will comb through the results with algorithms designed to catch the faintest, slowest moving dots. And somewhere in that ocean of information, a faint point of light shifting slowly against the stars might turn out to be the answer that everyone has been searching for. The search is about more than finding a planet. It is about resolving one of the deepest open questions in planetary science. Are the strange patterns in the outer solar system the work of a hidden world, or do they have a more mundane explanation that nobody has thought of yet? Until someone finds the planet or conclusively rules it out, the debate will continue in journals, conferences, and telescope control rooms around the world. Some researchers expect a resolution within the next 3 to 5 years. Others think it could take a decade or more. The timeline depends on where the planet is along its orbit right now. If it happens to be near its closest approach to our star, it will be brighter and easier to spot. If it is near the far end of its loop, it could remain invisible for years, even to the most powerful instruments ever built. There is also the possibility of a surprise. Rubin's automated systems might detect it before anyone specifically searches for it. A moving dot could pop up in the data stream, get flagged by an algorithm, and trigger a scramble to confirm it. In that scenario, the discovery would go to the machine that happened to look in the right direction on the right night. However it happens, one thing is clear. We are closer than we have ever been. The tools are ready, the data is coming, and the outer solar system is about to give up its secrets. But for now, the silence continues. And that silence says more than we might realize. Out past Neptune, past Pluto, past the scattered ice and the drifting comets, there is a silence that stretches for billions of miles. No spacecraft is listening there, no camera is watching. Just cold, empty space and the faint pull of gravity holding everything together at the edge of our star's reach. But that silence is not really silent. It is full of clues, orbits that cluster when they should scatter, a flat disk that warps when it should stay straight, ghost worlds on impossible paths that no known planet can explain, a cliff where the population drops to nothing, followed by a hidden population that should not exist at all, a calm inner core sitting untouched since the birth of the solar system, and behind all of it, a gravitational fingerprint that points to something large, something heavy, something real, circling in the cold where we cannot see. We have been staring at the outer solar system for almost a century now, first with Pluto, a tiny dot that tricked us into thinking we had found the edge, then with the Kuiper Belt, a graveyard of icy debris that revealed the edge was much farther away than we imagined. And now, with the evidence for hidden planets, worlds that reshape everything around them without ever showing their face to any telescope we have built. The search for Planet 9 and Planet Y is more than a treasure hunt. It is a test of how well we understand our own home. We built models of the solar system. We tested them against observations gathered over decades. And the models keep coming up short. Something is missing from the map. Something that bends the rules we thought we had figured out long ago. And that is the most exciting part of all. The realization that we live in a solar system that still has the power to surprise us. That 4.5 billion years after it formed, there are corners we have never explored and residents we have never met. The unknown is not out there in some distant galaxy. It is here, right at the edge of everything we call home. The Vera Rubin Observatory will soon begin scanning the sky with the sharpest eyes ever pointed at the outer darkness. Infrared telescopes will peer into the cold, looking for the faintest whisper of heat. Algorithms will sift through billions of data points, searching for one dot that moves when nothing else does. And one day, maybe soon, maybe years from now, a faint point of light will appear where nothing was supposed to be. When that happens, everything changes. The textbooks get rewritten from scratch. The models get rebuilt from the ground up, and a world that spent thousands of years circling in silence, unseen and unnamed, finally steps out of the dark. Until then, the Kuiper Belt keeps turning, the orbits keep bending, and somewhere out there, beyond the reach of every telescope we have ever built, Something massive is waiting. We just have not found it yet.